Benintendi. I'm just a chemical engineer with a Master Science in Environmental Engineering. I am located in the United Kingdom. I'm a fellow member of ICME, and I also have just an academic role at the ULB University of Bruxelles, Belgium. I have some international publication, 2 books, and both books are related to process safety. That is essentially the topic that we will discuss today. Okay, I've tried to just summarize in 3 main questions, essentially just to split into 3 main questions, essentially the coverage of the subject we are going to face today. The first is, what is process safety? That is important just to share with you and just to have a kind of common understanding of the wording. Wording is important, especially for those of you that have not been involved as yet in process safety jobs. So what is process safety? Just a second subject is role and contribution of process safety to chemical engineering research. And we will finish our discussion just presenting something about the ability in process safety calculus as a key driver of research. So what is process safety? This word is very easy, is very popular and familiar for people that work in engineering companies. But probably if we go into the word, we can find out and discover something that is could be very interesting, and especially could be very effective in just clarifying exactly what we mean, and much more than just the general meaning, the implications that such a word entail. Okay, I've tried just to condense the definition of process safety into 2 main lines: inherently safe design and acceptable risk. I have the illusion that probably these can just cover the 100% of the challenge and the difficulties that normally we meet when we try to be effective in resolving the roles and the problem of process safety. Okay, inherently safe design, we have to go back into the past and just to remind you, Trevor Kletz. Trevor Kletz was just a chemical engineer working for ICI, and in the United Kingdom decades ago. And after a couple of important incidents in the UK, first of all, Flixborough incident, he just created essentially the concept of inherently safe design that we can identify and define as a design approach with aims at eliminating hazards. That is, remember, hazard is a potential for harm, by implementing choices and process configuration consisting essentially of eliminating hazard sources, reducing the severity of consequences, reducing the likelihood of hazard occurrence, and separating or protecting people from hazards. So this is essentially the target. We have to go back just to probably focus better about the introduction of this definition into the process safety. 1974, it was Saturday, and of course, we know that the most catastrophic incident in the process safety history occurred during the weekend. This is not just a secondary thought. Okay, we had essentially a series of reactors that were managed by the Nipro plant company. We are in the UK, we are in England. And this process was related to the production of caprolactam from just through oxidation of cyclohexane into cyclohexanone. There was a problem. A junior process safety engineer that was on site in Saturday. There were not manager, no senior technicians on site. Just a junior engineer discovered that reactor number 5 was affected by just stress corrosion, and decided to remove the reactor number 5. We can see essentially some boilers. These are reactors, but in reality they are like boilers. And there was essentially the flow from the top to the bottom by gravity. And he found out that the reactor number 5 was affected by corrosion, but just the beginning of corrosion. Decided to remove. And the best he could do was essentially just to connect reactor number 6 to reactor number 4 with a dogleg with a gap between the axis of the bellows of the flanges. It was an absolutely big mistake. Okay, we can probably figure out what happened. In reality, there was essentially when the plant was started again. Okay, we are dealing with essentially 200 degrees C and something like that about pressure in terms of bar. So very potentially critical process condition. When the plant was restarted, essentially there was a moment that was essentially applied through the axis of the flanges that was initially balanced by an additional moment between consisting of two shear forces. The shear forces essentially ruptured essentially the bellows that were not designed to withstand the forces. And the problem was that in reality we had essentially released, there was a leak of cyclohexane at very high temperature. There was a witness reporting that the cloud started from the location of the reactors, the 6 reactors, and arrived at the so-called hydrogen location of the nitro plant. That was essentially the previous process configuration, where probably the cloud was ignited. There was a flash fire. Some witnesses reported that there was essentially the laminar burning velocity that governed essentially the flashback of the flame back through the plant site, and this was essentially the result. We were in 1974. Before that, probably the only incident that we can register in our records were just related to inorganic chemistry. So after 2 years, as you probably know, in Europe, in Italy, we had the Cevaso Incident, and after that we had some regulation that were essentially were introduced in the international regulation. Since the incident of Fixborough in the United Kingdom, control rooms have been built as blast resistant and located outside the disruptive explosion overpressure contour. We probably in the UK, we anticipated the introduction of severe and serious rules like this probably much earlier than in the rest of Europe. So what practically speaking, what do we mean with inherently safe design? Until 15-20 years ago, in order to reduce oxygen concentration in the boiled water, so boiled water, we have a blowdown. So we have feed the boiled water with new, essentially new demi water, and that oxygen is essentially just a corrosion promoter. So we have to keep the oxygen concentration. Until 20 years ago, more or less, I remember, because I worked as a process engineer in this field, hydrazine was added to water. And I remember personally, but hydrazine was used for a long time in boiled water as an oxygen scavenger, has been completely banned because essentially, as you know, this is the CLP regulation that is in Europe is the regulation that is used for classification, labeling, and packaging. And this toxic is swallowed, toxic in contact with skin, and so on. So this is essentially an example of one of the first pillars of the inherently safe design, replacement, substitution. Today, in order to essentially to achieve the same target, we add sodium or potassium bisulfite. So it is inherently safe because there is no longer a toxic chemical in the water. This is a way to comply with inherently safe design rules by travel plates. Okay, the second keyword to identify process safety is acceptable risk. Acceptable risk is not an easy, an immediate concept because we know that unfortunately we have to pay something to risk. We cannot reduce. There is essentially no risk zero in our project, in our design. So we have essentially to accept some risk. So acceptable risk, we can see here the UK ALARP diagram that is internationally internationally adapted and accepted as probably the most effective, just in order to identify a validated acceptable risk criterion. So acceptable risk is a second keyword. So just to conclude this first tile, this first, let's say, building block of the definition, we can say that process safety can be maybe identified as a discipline of chemical engineering, or of course also other, but I'm a chemical engineer, so I have just to promote chemical engineering, aiming at predicting and any possible hazardous process engineering deviated scenarios, potentially resulting in serious consequences for people, environment, and asset, encompassing viable techniques effective in minimizing the related effects and likelihood. I think this definition could work, maybe. Okay, why is process safety different from other disciplines, and what is the relationship between process safety and process engineering? Okay, in my experience, and I probably think you can agree with me, I think process safety is somehow just a daughter of process engineering, or a sister. We know that outcomes of process engineering strictly comply with the design specification implemented through the simulator, ISIS, for example, according to the license requirements. Any process deviations are predicted and properly managed by the control system to an acceptable extent. When we essentially carry out an hands-on study, okay, we can discover that there are some deviations, but in reality, if we have just a distillation column, it's not likely to can have a huge departure from the design specification. This is process engineering. Process safety, in my experience, I can recognize outcome process safety scenario present a much larger qualitative and quantitative uncertainty. The adoption of software simulators, predictive models, and any kind of additional tool is not as effective as for process engineering. The bunch of competencies required for process safety from process safety engineers is highly multidisciplinary, and the international regulation is essentially a way just to essentially require specific new techniques to be applied. International regulation is not secondary in the definition, because we have seen in the last, I would say, from the Cevaso directive introduction, that in reality, probably the contribution and the challenge of the international regulation, and I would say the European regulation, we could dedicate just a kind of specific discussion about the relationship between the European and non-European. The European regulation is strongly systemic, is holistic, whereas the American regulation has been predictive and additional. Okay, so ethics, for example, we will discuss about ethics. So the international regulation has been a forcing, terrible, huge, let's say, promoting factor for process safety. So we can see that process safety is somehow different from process engineering. The spread of competencies, the spread of knowledge is probably larger. It's difficult to say this is a scenario. This is possibly the scenario, we could say. Okay, so the second question, the second subject is, what is the role and contribution of process safety to chemical engineering research? That is essentially a subject that Savio has just put on the carpet. Okay, in order to cope with this specific subject, we have to consider what is the organization chart of a project. We can see just a summary of the specific areas. We can recognize we have a project director, we have a project manager, we have an engineering manager, and we have some disciplines. Okay, what is the peculiarity? Why is process safety engineer role so particular? As you can see, I've tried just to identify some specific relationship between these roles, also using a different color. In my experience and from the legal point of view, we can say that process safety, okay, all the disciplines report to the engineering manager. It's unlikely, even if it is not completely impossible, that a mechanical engineer, civil engineer, or process engineer talk directly to the project manager or to the project director. But the process safety The role of process safety is very particular because we are dealing with people, asset, and environment. So the process safety has the capacity, the ability, and also the power, somehow the power to, in addition to discuss directly with the other discipline, okay, in a meeting or just in the relationship of the task, also directly with the project manager from some specific aspect of process safety engineering and also with the project director. This happens. We can say that process safety engineers systematically share by nature their context with all the other disciplines, largely dealing with their subject. We can have some example. I have been working in my latest EPC contract in Middle East for 7 years with civil engineering, working about blast the buildings. So competencies must be really large. Blast design of buildings and equipment implies significant implications, which require and entail a large overlapping of competencies and knowledge. We can see here, this is the result of explosion. We must be able to understand and to have the same wording of civil engineering, because civil engineering competence, of course, is large, but is related to their specific discipline. So you have to be familiar with some additional concepts. We must be familiar also with instrumentation. You know that now functional safety is one of the most important, let's say, most important subject that we face in a project. So we must understand what does system reliability means. This is addressed in the process instrumentation design through the safety integrity level allocation of instrumentation loops. But we also have to discuss in terms of the legal and the regulatory implication also with electrical engineer, and in Europe also non-electrical equipment, so mechanical engineer. As the classification, electrical, non-electrical is a process safety engineering duty. So we can see also about this, we discuss with the process engineer, we discuss with instrumentation and control automation people. So in reality, process safety scenarios in complex projects are various and are strongly multidisciplinary. So we essentially deal with fire, with explosion, with toxicity, with blast, so structural engineering, layouting and spacing, so the layout, hazardous areas, chemicals, and emergency planning. So this can probably identify the range of the concept and the knowledge that we have to manage in order to be effective in a project like this. Last but not least is also the relationship with the manager. Why? In the previous slide, I decided to relate the process safety engineer with project management. As you know, the project engineering, the engineering manager is essentially related to the technical role and technical tasks, where the project manager is the registered office of the cost of the project. The alarm, so the, let's say, acceptable risk implication that we have discussed before implies some cost related aspects. This is not trivial, because in reality, unfortunately, when we have to decide essentially if and when risk is acceptable, we have to consider that it is essentially, let's say, an economical exercise. So we have to discuss with a project manager to identify what is the risk for asset, what is the risk for environment, what is the risk for reputation, and what is the, unfortunately, the cost of lives, the cost of people. You can see here just a picture showing essentially the so-called methodology that is called ICAF, that has been introduced in the UK, and also the major oil and gas company use it in order to identify what is the so-called disproportional factor that must be managed in order to identify when the risk is acceptable, is broadly acceptable, is not acceptable. So economical implication. In terms of project direction, we could, in theory, it's of course unlikely and difficult, but process safety lead is possibly the only one discipline leader entitled to stop the continuation of a project or of a production based on serious safety concern. In my experience, in order to, let's say, just to make everything robust and substantiate, I can tell you that I have been asked by a project director to fly from London to Kuwait Friday night to Saturday, because the project had been stopped anyway, and there was the need to identify exactly the solution for some problems, for some issues, and okay, the final green light provider was myself. So this is true. Just in order to show how is important is the relationship of the process safety engineer task with the other part of the project. Okay, so the tremendous growth of safety environmental aspect related to the advancement of technology and to the restriction and requirement of the regulations have progressively resulted in consolidation of process safety as a standalone discipline, contribution of new concepts, principles, and techniques, and the implication of chemical engineering research are huge. So, for example, just in order to have a practical landing on the topic we are discussing, carbon capture and storage. You know that the Kyoto Protocol has just identified some greenhouse gases that must be reduced, and more or less the different countries are now working in order to reduce by some specific dates let's say the concentration, the release of some greenhouse gases. Of course, the main enemy is carbon dioxide. Of course, you know the war, you know what's happening everywhere in the world. Okay, we can discuss about the real effectiveness of this, but in reality, this is essentially just, these are the gases. Carbon dioxide is, of course, by far the most important greenhouse gas to be reduced. I had some 3-4 experience about carbon capture and storage. And essentially, we can see here, for example, just an example of equipment that is essentially based on molecular sieve and membrane that was capable of removing carbon capture storage from methane. So essentially, it was a carbon capture. We can see here just the overall arrangement of the plant based on membrane, so carbon CO2. Okay, what is essentially the final let's say the final outcome of carbon capture storage? Generally, capture of CO2 can be applied to a large point sources, and CO2 can be compressed and transported for storage in geological formation in the ocean, in mineral carbonates. So it's easy to plan and just to foresee the way to remove and to dispose of CO2. We can see here essentially just as a kind of just multi-directional just disposal of CO2. But in reality, there are some problems that have come out when we have tried essentially to deal about carbon dioxide. Why? The reason was essentially because prior to implementing any carbon capture and storage regulation, the technology, the worldwide managed technology was related only to some specific threshold of concentration and the threshold and limitation in inventory. The new problem was essentially that starting from the carbon capture and storage new projects, of course, we were essentially forced to manage new let's say new horizons, just new tasks. So long pipelines have been designed entailing unknown risk scenarios for people, vulnerability, and environment. We will try to understand why unknown risk scenarios. The process characteristic of streams, notably supercritical conditions, have presented new process scenarios. Gas streams somehow behaving as a liquid with a new challenge for compressors and related equipment. Carbon dioxide phase transition is very particular. Below its triple point, the vapor phase is in equilibrium with soil. This causes potential critical process consequences for equipment and piping. Last but not least, this is very particular and probably identify very interesting research challenges and subject. Carbon dioxide equilibrium thermodynamics doesn't work very well or doesn't work completely. So it's very particular and differs from other ordinary gases. Okay, we discussed about toxicity and about unknown variables for, what do we mean exactly? Okay, we essentially know that the Haber's law identifies a toxic load. Toxic load for a chemical is a measure, is a product, and is a measure to essentially take into account the two main parameters. One is the concentration, and the second one is the exposure time. this specific this couple of variables can probably cover all the let's say the important parameters that we have to manage when we deal with toxicity. We know that essentially we can see that all the let's say the damage scenario for people, it's strange, but probably is I don't know, is a law of a universe. Okay, all the damage and the effect, the hazardous effect regarding fire, regarding blast, and regarding toxicity works according a probing function. The probing function is in reality is the function that you can see on the screen. So we have essentially just the concentration with an exponent, and we have the exposition time. Through the probing function, we can relate the probing function with a Gaussian, and we can identify exactly what is the probability, depending on concentration and exposure time, the probability of death or serious damage for people. Relatively low CO2 concentration or small stream traditionally managed in the chemical industry have excluded any relevant toxicity coverage in the probing function adopted for chemical risk. This is very, very weird, because in reality, when we try to understand what happened, for example, for hydrogen sulfide, we can see that using the probing function, we can moving from one exposure time to another, and depending on concentration, we can have a percentage of fatalities. In reality, the TNO, that is, one of the let's say holy monsters in process safety, is a very highly reputable institution, has just provided many years ago, much earlier than 2005, maybe in the 80s, okay, the list of the A, B, and N that are the constant of the probing function, in order to enable the process safety engineer to arrange the probing function and to identify exactly, let's say, the percentage of that. As you can see here, we don't have a carbon dioxide. This is just let's say a strange weird thing, because in reality carbon dioxide is a gas, so we have probably we can expect some specific let's say threshold of toxicity. In fact, the UK Health and Safety Executive, they have been working just in order to complete the list, and they have introduced slot and slot. So the Health and Safety Executive has been just a very strong research program. After that, essentially the carbon capture storage has been introduced, and in the UK there was just a national grid program. So the carbon dioxide, as you can see now, according to the UK Health and Safety Executive, can rely on a specific probing function. So this is essentially the result of a specific toxicity research. All the other institutions, including TNO, has been working on CO2, because the problem was, if we have a release, if we have just a leakage, how can we prepare our safety plan if we don't have any validated? So this is an example how important is the chemical engineering research regarding process safety for toxicity, the new challenge, the new technology, the new regulation. Okay, this is the pressure enthalpy diagram for CO2. We can recognize, I think we can probably have, okay, we can here have the zone of liquid on the left-hand side of the slide. We can have the vapor liquid, equilibrium zone in the center, and we have a triple point. Triple point should be around the 5 bars. Below 5 bar, we only can have essentially a vapor-solid equilibrium. If we can see here, we can see here how the carbon dioxide reinjection has been planned in the UK. I attended some specific project, and so I've been working about the carbon capture storage related to the national grid in the UK. It's important just to focus on this diagram. In reality, normally, for example, I work in Malaysia about carbon capture storage, and I remember that in reality in Malaysia, the Petronas are planning to implement carbon capture storage for their plant, and they will be managing supercritical flow. So this is essentially the condition. We should be around maybe 80 bar, okay, and we have supercritical flow. So if you now just think about just a pipeline, you can see essentially a supercritical carbon dioxide flowing. Supercritical flow means that it's a gas but behaves as a liquid to its very high density. Special pumps are required, and there was not memory, so there is the research and development, department of Petronas. They've been working a lot in order to identify exactly the process condition of just supercritical carbon dioxide. So carbon dioxide pumping has posed a new operational issue. And once again, chemical engineering research has been working and is still working about what is the best operating way to flow, to manage and to pump liquid or supercritical. So this is very specific. There was no memory about. We can see here essentially we have a compressor, and we essentially have just the ordinary process line. This is 30 meters per second is the velocity of the CO2 that is going to be essentially flushed downstream. But we also have here essentially a pressure relief valve that is able just to vent CO2. Of course, we are in sonic condition. Okay, we have sonic condition. So expectedly, our velocity, if we have the pressure relief valve operation, is about 300 meters per second. Okay, I remember that I had just a specific discussion with the process guys, and they applied ICIS. ICIS said, okay, you have an isenthalpic, because you can have just the Joule-Kelvin, Joule-Thomson effect. It is isenthalpic if you have essentially a release through the pressure relief valve. Because by memory, okay, the previous memory of the simulator was, okay, it is an isenthalpic, so the downstream enthalpy is the same as the upstream enthalpy. So process simulator foresees an enthalpic expansion according to JT throttling transformation. But we know that in reality, the Joule-Kelvin, Joule-Thomson, let's say, equation that we can see is obtained from this equation that is essentially the law of conservation of energy for open system. We can conclude that we can have an isenthalpic transformation, but provided that the velocity are the same. Otherwise, in reality, we have essentially a different value of the enthalpy downstream. In reality, we have essentially that if we consider that we are starting from 30 meters per second and we arrive at 300 meters per second, probably we don't have an isenthalpic. We can have essentially just a slope for regarding the transformation line, and we have the risk to enter the solid formation zone. This was a problem that was not in the memory of people and required a specific research approach just in order to adjust the calculation. And in reality, expansion in carbon dioxide stream can result in solid formation, plugging, and embrittlement. Accidental releases to atmosphere pose serious uncertainty in the prediction of dispersion outcomes, both to the solid formation and to the specific thermodynamics of carbon dioxide. Carbon dioxide does not follow strictly equilibrium thermodynamics due to longer relaxation time compared to the ordinary gas. The last sentence is very important. Is so important that there was a 12 million pounds research regarding CO2 carbon capture and storage that was led by University College London, and the challenge and the final objective was just to try to identify what happened if we have a release from a long pipe, because there was no memory. There was many differences regarding the behavior of CO2 because there was no memory. So this was an integrated multi-scale modeling approach for simulation of multi-phase dispersion from accidental CO2 pipeline release in realistic terrain. This is essentially the flow chart of the project. We can jump. This is very important, and it's probably the heart of our discussion that we are going to finish. And we can see here that in reality, the blue line is the line that probably we can expect to follow if we apply equilibrium thermodynamics. What the researchers discovered regarding this project, the CO2 pipettes in China, there was a long pipeline, industrial scale, that was operated in order to understand, and there was a simulation of release. And there was measurement regarding essentially the behavior of CO2. And they discovered essentially that in reality, there was a significant departure of, let's say, CO2 in terms of the vapor and vapor solid, because here we are below the triple point. There was a kind of oversaturation. We can follow the yellow line because the relaxation time, that is the time taken by the CO2 to follow just a phase transition. For example, if we have nitrogen, oxygen, or if we have water, and we are follow of transition, we can probably expect some time in order for one phase to move to another phase. In this case, we have essentially a much longer time. So they experienced essentially an oversaturation, accumulation of, let's say, higher concentration of a vapor mass that was not expected adopting the equational state of the carbon dioxide prior to moving to the solid. This was essentially obtained just thanks to the research program. It was a long multidisciplinary program that was essentially aimed just to understand exactly what is the behavior because there was no memory. I just played about this point, and in reality, was very nice to me to try to have a kind of theoretical model to explain why is carbon dioxide so different, and why when you are going to have just a plant and you are feeding carbon dioxide, you can expect to have some strange and unexpected behavior that can impact, that can be really serious in terms of the equipment health, but also in terms of process safety. Okay, I'm very fast. Carbon dioxide can undergo bleeding because, of course, it's a liquid, and if we have just a catastrophic failure or collapse of tank, a ruptured tank, we can have essentially just an expansion. And going on, we can just close this discussion, presented fluid curtain technology. Fluid curtain technology is essentially just a process safety mitigation system that you can adopt when you are in presence of some specific hazardous chemicals such as H2S, ammonia, CO, HCN, HF, and others. And your risk scenario doesn't comply with risk limits. So prevention doesn't work. You must mitigate. Okay, I personally have just been working a lot about this for 3 years in my last project, and the peculiarity of this specific system and process is that this is a plug cross flow reactor that works according to the Ftenakis model. Professor Ftenakis is a professor of Columbia University, and I've been discussing with him after my just some publication, and you can see that it's unlikely that you can have this specific process reactor configuration in process engineering. So I could say that this is specific for process safety. So it means that just a specific dedicated research program for just a reactor configuration like this can just result in being effective, because normally this is an open space reactor. You have essentially just release of leak of H2S ammonia, and you can have a specific configuration that you can follow here. That is not very easy to design, because must work according to very specific parametrical range, and you can have a reduction. You can remove preventing the release from impacting on people and environmental by more than 99%. This is a specific configuration of reactor configuration that belongs to process safety engineering, and still requires a lot of research efforts in order to extend. I probably maybe the chance to adopt this technology for H2S. Typically, this has been applied in the past to HF. You can see probably there was okay. You can see here the picture. This is maybe Aramco. In the alkylation project, you have HF, and there was a very lucky and effective adoption of fluid curtain for HF. There was no memory for H2S, and there was a big project in the Middle East, and I've been working a lot in order to adjust because it was different, especially because H2S cannot the every coefficient for absorption is not good. So we have to work a lot, and we carried out a research program in order to adjust and to adapt this specific cross-flow reactor configuration to H2S. This is an additional example. Here you can see the thermofluid dynamic. The fluid dynamic part is very important. If you fall outside the range, the system doesn't work. So this is very, very difficult and requires a lot of study. Okay, now we conclude with 3-4 slides. So ability in process safety calculation, a key driver of research. We can conclude. Process safety scenarios imply unusual complex process configuration, which cannot always be managed according to the techniques of process engineering. This entails, in turn, the possession of specific calculus capabilities not necessarily supported by software and calculation tools. So the process safety engineer must be very, very clever in calculation. Process safety condition may be extreme in terms of thermofluid dynamic features and present a high degree of novelty and unpredictability with respect to development of the techniques of ordinary engineering. Specific areas of engineering require a specific strong impulse of applied research to cope with the requirements and objective highly demanding regulation, risk limit, multidisciplinary context of involved subjects. So, what is the panel of competencies? I think material science, thermofluid dynamic modeling, inherent safety approach, risk management, technical regulation and standard. Here we can see a kind of just a conclusive summary. What is the relationship between an ordinary route of the process safety engineer task and the research? And okay, we can say that we have normally a context. This is also consistent with my experience. We have some process safety requirements. Typically, we can have, it doesn't happen always, but we can have unresolved issues and new scenarios. So we have a research horizon. We are forced to essentially face new approaches. What is the final outcome of a new approach? Can be new technologies and the new safety techniques. So we can essentially split the final outcome of let's say the research in process safety. We can have the final gain that we can earn. We can have a final gift that consists of new technologies, means new technology also, let's say, other than process safety. No, we can have a lot of new materials. We can have a lot of new technicalities, new process configuration coming from the process safety scenario. And we can also have new safety techniques themselves. So working for, let's say, process safety in order for making process safety more effective. For example, and I conclude, this was essentially the previous ATEX, IEC, and European norm. Until 10 years ago, you used essentially the low explosion limit, and you have absolutely huge cloud that were absolutely ineffective because you were using a low explosion limit, whereas normally you don't have a low explosion limit that is very low concentration. That means big cloud. And so there was a kind of just a revised ATEX standard. I am really proud to have a part in this revision, because in 2010, I essentially discovered that the turbulent jet modeling for Zadar-Zerah classification, due to the air entrainment, reduced the concentration. So the adoption of a low explosion limit was an absolutely huge, let's say, serious drawback for the company, because you had huge hazardous areas. In reality, if there was the Health and Safety Executive in the UK, they carried out another research program using Fluent, CFD, and they discovered that in reality, the real cloud, due to the air entrainment, was much smaller than the original. So this is essentially a clear indication on how ability and process safety calculation and the execution of a research program was effective. Now there is a new standard that is used with much smaller. You can see here they recognize the effectiveness of my publication, and this has been incorporated in the new standard. Okay, the last one is I think it's interesting because during HAZO there was a very important licensor that essentially explained that in reality HCl that was used in the Penex process, isomerization process, could be flared, and there was no conclusion about what was the outcome of this. So I remember that I say, okay, what about HCl, so hydrogen chloride to the flare? You can have some problem. If you are lucky, you can keep hydrogen chloride, but you can have also Cl2. They were completely silent, and they recognized that was a part of the technology that probably was not complete. After that, they were on just trying to cope with the problem, and they essentially worked about just the equilibrium, the equilibrium of Decon, that is essentially the equilibrium between Cl2 and HCl, in order to find the best working point of the process in order to reduce any kind of risk. Okay, thank you very much. I hope that just to not be too long, and I am happy just to discuss with you if you want.
Thank you, Renato. Thank you for the presentation, for accepting our invitation. It was a lovely and comprehensive presentation. We have a few questions here that now we're going through them, and we're going to discuss a little bit. As I told you before, there's a bunch of people here from undergrad, graduate students, and researchers. So just assuming that the questions are going to be pretty mixed. But the first one goes like this. One of the students, undergrad students, is asking, as far as the fluid dynamics is concerned, probably he's taking this course as this semester, how important is the basic fundamentals of fluid mechanics in the context of process safety?
Yeah, it's a very good question. Fluid dynamics in particular, Savio, yes? Fluid dynamics, okay. It's a very important question. Sorry for not addressing this in reality, but I was very careful about your time. So as you know, because you have been I hope you have been able to use my book to sleep very well overnight, but in reality, I dedicated my first 6 chapters of the book to fundamentals, because I found out that in reality, even if we are chemical engineers, so we essentially have just a kind of background preparation that should cover everything. But in reality, there are 2 points. The first one, some specific subjects are not probably necessarily just for economical reasons, not completely covered during the studies. And last but not least, some specific chapters are not specifically addressed to process safety. One of these, for sure, is fluid dynamics. Fluid dynamics, okay, I graduated more than 35 years ago. And so it was very robust, and 5 years in Italy was very, and I remember I had a very good preparation in fluid dynamics, but in reality, I recognize now it is not enough. It would not be enough. It would not be enough for 2 main reasons. The first one is the complexity, absolute complexity of the scenarios that we have to cope with. Let us not forget that normally we deal with release. So we have loss of containment. Loss of containment means that we are essentially not in the position to check, to control, let's say, the fluid dynamics regimes. We know, for example, how important are parameters like Reynolds number and the entrainment. And normally we have some specific regimes after a release. We have the Mach disk, so we can have some specific speed that are higher than the sonic speed. We are hypersonic. So the gas dynamics, that is a specific subject of the mechanical engineer, and aeronautic engineer, is important. I had to go into the gas dynamics in order to become familiar. And then you have to consider that you have to quantify what happens after the first 5 meters, the second 5 meters. You have to consider how important is the dense gas. Sometimes you can have essentially a gas that is ammonia, but after the release is very cold, so is lighter than air, but in reality behaves like a heavy. So I would say it's a very good question. I probably would say that the fluid dynamics is one of the pillars, particularly fluid dynamics, let's say, tailored to process safety. You should, if you want to, if you really wish to deal with the process safety, you must be sooner or later become familiar with some specific rules of fluid dynamics tailored to process safety, because otherwise you can have a big mistake in your approach. And this happens also when you run softwares. A software sometimes, because software is a car. It depends on the driver. If you have a good driver, you can have a good response. And sometimes the software, even if they are good software, they cannot cover all the fluid dynamic notions.
Yeah, indeed. Yeah, I totally agree with that. In the same subject, Renato. As you mentioned, your book is a reference book in the process safety course here, so we use it throughout the course. And one of the students just called my attention for the bell shape that occurs in the region very near to the leak orifice. And then his question is, when you go and you try to model gas dispersion using CFD, quite often we ignore the fluid dynamics in the region very close to the leak where this bell shape is formed. And we kind of move the boundary condition a little bit downstream the release, because we are at the end of the day interested in the gas concentration as it disperses and not in what is going on in the region close to the orifice. So in that sense, in your opinion, do you think that the modeler that's operating the software, it's, let's say, it's committing a very big mistake in ignoring this bell shape, or it's something that needs to be taken into account when modeling CFD scenarios?
Okay, it's a very specific question, because we are zooming the part of the release that is in reality very close to the orifice. And you know that we have essentially we have a distance over which very complex and somehow unpredictable phenomena happen. I have tried to anatomize, to carry out a kind of anatomy of what happens when you leave the structure, the pipe, the tank. And in reality, I think that you can be affected by significant mistake. Of course, it depends on the liquid, on the fluid that we are managing, because of course, for example, just in order to provide you with an example, I will not mention, of course, the company, and I will not mention the client, of course. We have seen, for example, that there was a very important project in Middle East, and they modeled it essentially with an important software. I don't mention software for I don't know how did they let's say manage the software. So probably I don't know if the mistake that we found was related to the software or was related to the way but in reality they found that HCN, liquid HCN, had been just released, and the temperature was down. Was so low to reach -40 that was absolutely impossible. impossible because this can happen for example, for LPG. So I would say, generally speaking, if you carry out a CFD study, I think you can be of course you can be probably entitled to have some more words if you compare to the use of software. For what regard the bell shape, particularly the bell shape, you know that in the book you can find, and in the literature there is a big discussion about, you can find essentially some specific validated the range over which you can assume that you can have essentially the development of specific regimes. And for example, CCPS provides some specific guidance, because the problem is if you carry out just a CFD model, or if you can use some software, or if you can use, for example, OpenFOAM. Probably you can know OpenFOAM, that is probably the only one CFD tool that can be comparable to Fluent. And the thing is that you have to validate what you are doing. That's a problem. So if I speak to you as a process safety engineer, as a process safety manager, I must validate your final conclusion. We know that essentially we have some specific range over which you have the MAC disk. After the MAC disk, you enter that is the underexpanded zone, when you can exceed the sonic velocity, the sonic speed. Then after that, you can assume that you have essentially just the sonic velocity again. Then you can reach the Gaussian zone. The mistake that you can of course you can be affected by a mistake depending on the assumption that you do. The problem is the complexity can be very high, because normally when you carry out the fluid dynamics calculation, you must consider the thermal effects. You must consider, normally you have in the book, you probably find let's say the profile of the concentration, the profile of the temperature, and the profile of the velocity. And you have to come together, and it's not easy, of course, to have a regular approach for this. So when you are involved in real project, typically you should comply with validated rules, because the validated rules are important because they are defendable. Otherwise, you must work a lot in order to just to accommodate together the different profiles and the different parameters of your work.
Yeah, absolutely. There's a couple of other questions here. This one comes from one of my colleagues in the department where I work, and then she wants to hear from you. She works with a process control, so she's asking, in your opinion, the advanced process control, what is the role of the advanced process control, and how it can deal with process safety, in your opinion?
Okay.
She mentioned, just one sec. She mentioned one more thing, Renato. She says what she really means is that considering that the process design can't be modified, so you have something which is frozen there, and how the advanced process control can be related with process safety.
Yeah. Okay, I think that the application in the real project are, of course, have become absolutely ordinary. And I would say the relationship and the implication and the relationship between the advanced control and the process safety are huge. I think this is, I could be wrong, or I could be partially right, but I think that in reality, when we carry out a SIL review, when we are involved in SIL allocation, and so when we are involved in loop in complex loop architecture, Normally, this exercise is carried out in a very, very automatic and ordinary way. But in reality, I have been involved many times in a specific question coming from instrumentation people and automatic control that forced myself to have a specific focus, entering the control architecture much more than typically you can expect to have in, but especially for process safety engineers that are very clever managing let's say the functional safety in terms of the application of I don't know, Excelentia and the other software. But when you have to carry out the reliability, the reliability exercise applied to complex control and advanced control is completely a different story. So I would say it's very important, and I would say that implications are huge. I have tried to explain why is the role of the process safety engineer so difficult, and in my opinion, I have been working in the last 10 years as the discipline knowledge owner for Fossewiller UK. So it was a very, now I know now it's no longer Fossewiller, now it's EMEC and then Wood. But many projects after third-party review, and I also was involved in third-party review regarding the control and the advanced control, and regarding also essentially the process safety times, and regarding the relationship by different loop, and regarding the cascade control, everything, we found out British Gas and BP and probably another British company, they assigned just a third-party review, and we also looked into this part of the work, and we found a lot of areas that were not very clear. So I would say that is very important, this, and sometimes is not covered by process safety engineering, but should be covered by process safety engineering.
Yeah, absolutely. We have one last question here. Let me get it, just one sec. It comes from one of the research students. He's asking, in your opinion, what is the next step in the research as far as process safety is concerned? What is the future?
Yes. Okay. I'll try to complete my answer. The answer that I have provided. Okay. It's thank you. It's a very good question. I'm very happy to be able just to brainstorm this. My last slide was in reality related to this question, because you normally go through the ordinary route of a just process safety task, and we are discovering in the, I would say let's say the rise of these consideration started 1st July of 2003. In the 1st July of 2003, the ATEX regulation was implemented in Europe. All the electrical engineers that they supposed that the ATEX was just the new chapter, no, the revised standard of the previous approach, but they were definitely wrong, because the ATEX has introduced a comprehensive set of disciplines into the specific objective to prevent ignition. And so it was completely different from the previous standard. Just to tell you that in reality, the challenge that the regulation, in Europe, we had essentially, I don't know in the US and in South America, but in reality, now in Europe, the regulation is forcing companies to move, just to adjust their knowledge, and just to speed up and implement research program inside the companies, especially the manufacturing companies, just in order to comply, because otherwise the production cycles are no longer cost effective. ATEX is a universe. There was a essential, especially for the non-electric equipment. Just an example, ATEX could be let's say the subject of a specific seminar. You now have to consider the Peltier effect, the corrosion, just for example, the electrochemical behavior of material. When you are just using, for example, gaskets or balls, and you discover that you have to consider that you have to maximize or minimize. So this has resulted in overflowing a lot of new research. So I would say regulation, specifically European regulation. Why? Because from 2000, European regulation starting with there was a new approach. So we had Cevaso Directive, Machinery Directive, the Pressure Equipment Directive, CLP, Classification, Labeling, Packaging, and you have ATEX, you have REACH regulation. Now, the material safety data sheet is no longer 4 page, 3 page, 1 page, half a page, must be 20 pages, because otherwise the Helsinki European Chemical Agency doesn't know to register your chemical. And so this was terrible, because when the REACH regulation was implemented, the QSAR, that is essentially the computational toxicity approach that can replace the in vitro animal test, allowed the company not to be involved in a absolutely cost ineffective research for toxicity. But there was a review. So I think that the future of process safety will be comply with the new rules that you have seen the carbon capture and storage. There was 12 million pounds research in China by 12 university. And what is more, considering that in reality the process safety requirements are more and more demanding, you are forced, in order to comply, just to think in a different way, just in order to comply with the more stringent rule. For example, now in Europe we are 10 to minus 6 per year. So in terms of the acceptable risk. So this means that probably if you apply the process engineering as it is, you probably are never in my last experience, you are never in the position to comply with the rules. So it means that in a way or in another way, you have to go to the literature, you have to study, you have to probably just to create a new model, and you have to think in terms of novelty of technology in order to comply. And this is not happening only in Europe. You consider that a very important point, outside Europe, now in Middle East, the European regulation is becoming the standard, even if it is not mandatory, but it's becoming the standard. So it's completely trivial that you are not in Europe, because the Arabic and the Middle East people saying, no, we want that. Dust explosion was not in the US. In the US, the dust explosion was not exactly included as just a process safety and regulatory item. In Middle East now, dust explosion must be considered, and they are using a European regulation. So I would say regulation, new technologies coming from the application, and new techniques. This is producing a completely huge separate research program for process safety engineers.
Yeah, I agree. Renato, it was really a pleasure to have you here. I would love to spend the whole afternoon with you, although it's evening in the UK. But I guess we're running a little bit late now, and people, they need to go back to their activities. There's a couple of other questions. I will send them to you by email. Once again, I would like to thank you very much for accepting, for sharing with us your knowledge and your time. It was really, really excited. I know that's been more than 10 years the last time that we met, so I hope that we have a chance to meet face to face soon. That would be lovely to have you here in the department as well. Let's try to organize that, so then you can spend 1 week in São Paulo and maybe teach in one of our courses, particularly because, as I told you before, your book is the reference book in the process safety.
Obrigado. I am a little bit embarrassed because to be honest, Just 5 seconds. I carried out a course, a process safety course in the UK. All process engineers, and after that, Elsevier went to me and said, "Do you have any?" And so I decided to propose, but I was essentially kidnapped for 2 years, and my wife was not very happy, something like that. So it was. Thank you, Sofor. I'm very embarrassed. I'm honored, of course, to be a reference for your students, for you.
Oh yeah, yeah, you are indeed. You are in the library of the university, main library. We have a few copies of your book as well, so the students, they can get hold of them. So yeah, indeed, it became a reference, and I'm very happy with that as well. And again, thank you very much indeed for being with us.
Samuel.
Yeah, and I hope to see you soon.
Thank you, obrigado.
Okay. Yeah, you take care. Ciao.
Bye.